So, as you now know, not all science is based on hypothesis testing. Descriptive science starts from ground zero with no hypothesis and then gathers observations to generate conclusions. Nonetheless, the testing of hypotheses is still a very important part of what goes on in the natural sciences, so it merits a bit more discussion. The process of testing a hypothesis follows a series of steps that are commonly referred to as the scientific method, laid out in this flow chart here. The scientific method starts with an observation that sparks a question or introduces a problem. You then move to propose an explanation, a hypothesis that answers that question. Following that comes a prediction based on your hypothesis, and then an experiment to determine whether the prediction bears out, meaning that the hypothesis was supported, or if the prediction does not bear out, then the hypothesis is not supported. Let's take a look at this in the context of a real world problem. Let's say I walk outside to my garden and my tomato plants are wilting. I've just made an observation. Naturally, the next thing that happens is I ask a question. Why is this happening? There could be many possible explanations ranging from issues related to soil pH, too much direct sunlight, but let's say the explanation that I propose is that the aren't getting enough water. That's my hypothesis, a proposed explanation of the phenomenon. Next, I make a prediction. A prediction often comes in the form of an if then statement. So, in the context of this problem, my prediction would be that if I increase the amount of water provided, the plants will recover. Next comes the stage where I put my hypothesis of um, of increasing the amount of water to the test. I increase the water to half of the plants, and for the other half, I don't change the amount of water they are getting. Now that might feel wrong. You might say that in order to save your tomato plants, you should increase water to all of them. And that might be what you do in real life. But if we really want to approach this problem like a scientist and figure out an explanation for this phenomenon, with certainty, we have to set things up this way. And I will elaborate on why momentarily. But let's say we run the experiment and the results show that the plants that received more water recovered, while the plants that kept receiving the same amount of water were unchanged. This means that our hypothesis is supported, and the conclusion or the result is that insufficient water was the cause of the plants wilting. Now, as promised, let's revisit that detail of how the experiment was set up. Half of the tomato plants got more water, the other half did not. Effectively, what we've done is divide the tomato plant population up into two groups, where one group gets the treatment that we are testing out, meaning more water, and the other group does not get the treatment we are testing out. In an experiment, the group that gets the treatment that is being tested is called the experimental group. The group that does not get the treatment is called the control group. The control group is very important because it allows you to say definitively whether the treatment being tested on the experimental group is the cause of any changes. For example, what if you increase the amount of water to half of the tomato plants, but all the plants recovered? That would tell you that wasn't actually the water that made a difference. It must have been some other factor, because even the control group recovered without a change in treatment. If the control group wasn't there, then you wouldn't be probably conclude that it was the water that did the trick. But that conclusion would be incorrect. So this is the power and importance of including a control group when you are running an experiment and testing a hypothesis.